if I told you this tiny metal fridge magnet is a direct proof of special theory of relativity? And what if I told you the magnetism isn't real? It's just a relativistic twist of electricity. If you're wondering, or if you're shocked, hang on. The explanation is coming up right now. Right. How can I start? Okay, now let's consider a charged particle sitting next to a current carrying conductor. As you can see now, there is a charged particle. Let me consider the charge of this particle is plus, and it is sitting next to a current carrying conductor. Right. Now, at first, the charged particle is at rest, and imagine now charged particle is no longer a charged particle. It's you. You are here. You are the charged particle. You are carrying a charge, and your charge is plus, and you are just observing how the electrons are flowing. While you already know that the lattice ions, which are the plus charged lattice ions, are at rest. Right. Now this moving electron flow here. When you observe the moving electron flow, you are already there in the stationary reference frame with respect to the current carrying conductor. You are at rest. Right. Now, with respect to this rest frame, what you observe is there are some number of electrons. The charge density of electrons is exactly equal to the charge density of the plus ions that you see in the lattice. Right, there's no problem yet. Now, this is the point where the problem is coming up. Right, now imagine the plus charge, which means you start to move. You are no longer at rest. Now we already know that we can apply Fleming's left-hand principle to find out the direction of force. I'm going to explain, and you can later check whether my explanation tally with the Fleming's left-hand principle. If not, you can let me know, but I'm pretty sure that's going to work. Right, now take a look at this incident. Carefully observe what's going to happen here, guys. When the charged particle, which means plus charge, starts to move, it's no longer there in the it's a different reference frame. It's no longer there in the current carrying reference frame, because with respect to the current carrying conductor, the charged particle is moving now. Right. Okay, now he's in the meantime, now it's no longer a charged particle, as I mentioned earlier. Now it's you. Now you're observing the electrons and the plus charged ions which are there already in the conductor. Right, so we already know that we as human, or as people, we think that we are always correct, or like that's your what we observe is always we are at rest. With respect to us, we observe everything in the universe. So similarly, now here we observe what's going on, and here we see that with respect to us, the electron, actually we are not move as fast as electrons yet. Let me consider that we are moving a bit slower than electrons, but with respect to what, we still see that the electrons are moving as we are moving in the direction of electrons. We are still seeing that the electrons are also moving, but with a slower speed towards, according to my diagram or my animation, they are moving towards the left direction. Right, but in the meantime, he sees that the plus charges move in the opposite direction at a greater speed. Right, now this is the point where the relativity is going to play its role. We already know that, guys, according to the length contraction. Now when the electrons the speed of the electrons is quite low compared to the speed of the protons with respect to the observing with respect to you, as now you are the plus charge particle here. So what you observe here is now the space between the plus charges is getting closer because of the motion, because of it's much faster according to the Lorentz contractions. I'm going to show you now mathematically how Lorentz contractions work. So electrons are getting, the protons or the plus charges, not protons, actually plus charges is a better term, the plus charges are getting closer to each other. So as a result of that now, but you see the electrons are also there, but electrons are not as fast as the plus charges. So therefore electrons are they also contract, but the proportion is relatively lower, right? So now the plus charge, according to the plus charge now, as this moving plus charge observes, the positive charge density of this conductor is greater than the negative charge density. So it doesn't observe anymore the neutralized nature, because it sees that the charge density of positive ions is greater than the negative ions. Now, with respect to this moving charge particle, which is you see a plus charge which is there next to you, right? So what's going to happen now? Then obviously you will be pushed away from the moving conductor. This is not moving conductor, current carrying conductor. So this is the idea that you really need to understand here, right? But imagine now there's a person, now that's your friend. Imagine now that your friend is at rest at the lab frame, or you can say he's at rest unlike you, but he's wondering because out of nowhere, without having no reason, you're just moving away. There's a force on you, acted upon you, away from the conductor. He might be wondering. To explain this, he needs to have another way. So what he uses here is he's going to think more, and he's going to suggest that there must be another interaction among you two. As a result of that, you are pushed away from it. So he's going to put a name. The name is magnetism. But with respect to the moving charge particle, which is you, there's nothing called magnetism. This is just an effect of what? Electricity. This is it, guys. Thank you for joining today. Let's see you with another nice video, guys. This is my third part of this video series. Hang on, the next video will be uploaded soon.